Hi everyone. Let's do this Euler's method problem. My big thing recently has been when you're studying, don't try and remember the steps that you're supposed to do, because the steps will change depending on the problem. Instead, you want to understand what's the underlying concept. You want to have a simple way of thinking about what the idea is, because that's going to help you figure out problems you've never seen before. So, what is the idea of Euler's method? The purpose of Euler's method is to let you approximate a solution to a differential equation where you can't actually find the solution equation. So let's look at this example. This is an example where you could actually solve it, but let's pretend we couldn't. So we've got a differential equation, and I know that this is a point on my solution. So here's the information that we know so far, if I was going to graph it. We know the point 2, 1 is a point on our graph, and if I plug in x is 2 and y is 1 into the differential equation, that tells me dy dx, which is the same thing as the slope. So this is all the information I have about my solution curve. It might curve away like this, it might curve like that, it might curve like this, I'm not sure. Okay, let's take a look at and see what the actual solution looks like. So here's what the actual solution curve looks like. And again, the thing that we want to find is we want to find the y value in x equals 3. So if we actually knew what this equation was, of course we could just plug it in and solve it, but the whole point of Euler's method is you want to use it in situations where you can't solve for this directly. So one thing you could do is take that tangent line, like we know a point, we know the slope, because you plug into the differential equation to find the slope, and we could use this single tangent line to approximate the value. Well, clearly, if I use this line to approximate the value at x equals 3, that's pretty far away from where the true solution lies. So, this is the heart of Euler's method. For Euler's method, you don't use a single tangent line. You use one line to approximate the y value just a little way along, let's say at 2.5, here. And then you construct a second line that's supposed to be parallel to the tangent line of your original solution curve, and you use this second line to approximate the value you actually care about. And of course, there's nothing magic about 2. We could have gone 1/10 of the way and then constructed a line, and then another 10th of the way and constructed another line, and then another 10th of the way and constructed another line. So that's the idea of Euler's method. You're going to construct a sequence of tangent lines that follow the original solution curve. So let's take a look at what this looks like. I know I have a point that's on my solution curve, and I have a slope, which I got by plugging into the differential equation. So my slope when x equals 2 and y equals 1 is, let's see, 2 divided by 1 is 2. So I think point-slope form is going to be a good form of a line to use. So here's point-slope form. So for my first line, its equation is going to be y minus, let's see, y1 is 1, my slope is 2, and x0 is 2. Okay, so that's the equation for this line right here. Okay, and I'm going to use this to approximate the y value that's one step over, and my step size in this problem is 1/2. So I want to use it to approximate the y value in x equals 1/2. 2.5. So let's do that. I'll plug in 2.5 here. So 2.5 is the same thing as 5/2. And I want to figure out what's that y value. So let's see. 2.5 minus 2 is 1/2, times 2 is 1, plus another 1 gives me a y value of 2. So this is now going to be 2.5 by 2. Okay, so what we want to do now is construct another tangent line starting at this point. So I'll do that same process again. I've got a point at 2.52. My slope is going to be given by my differential equation again. So if I plug in my x value divided by my y value, that gives me the new slope. So let's make another tangent line. So y minus, let's see, I'm constructing it based on this. I'm constructing it based on this new point here, so my new y value is 2, my slope is this, my x value is 2.5, and so now we want to use this second equation Here's L1, here's L2. So we want to use the second equation now to predict what is f of 3. Because our original concept was we don't know what the solution curve looks like, but we know it's probably going to be something like this because the tangent lines are going to be following my solution curve because they're based on the original differential equation. So now I'm going to plug in the x value I care about, which is 3. And then you can work this out. So let's see, this is 5 halves divided by 2 is 5 fourths. 3 minus 2.5 is a half. So that's 5 eighths. So that's 2 and 5 eighths. And that's all there is to Euler's method.